Right, good day everyone. I was supposed to start this earlier, but I've been having some issues with my Microsoft account. Let me just do something real quick. Real. Alright, so here's what we're going to do today. We're going to try to understand polar form and argon. Wait, let me see. Let me make sure I can see it. Yeah, so we are gonna learn how to understand the polar form and the argon diagram. Now, this involves that we obviously know what a complex number is composed of, and we know that such complex numbers are composed of two things: an imaginary part, well, a real part. So let a complex number be Z. That's how they're represented. So it's easily identifiable. And equal to A plus BI. We have ourselves the real part, which is, our normal number system, it's 2.5, 300.5, whatever that number is. And then we have our imaginary part, which in itself is a real number value. It could be 100.5, same thing, but it's the coefficient of I, which is the imaginary identity. Wait, imaginary identity. Wait. Imaginary unit, my bad, unit. You could think of it like a vector, a unit vector. It basically represents one imaginary part, and B represents how many. So if you have 3i, you have 3 imaginary parts in total, right? Now, here's the deal now. They want to play a game, and that game is to, for some reason, out of none of the blue, let, I don't know, B, Y, and let A, B, X, and plot that on a graph. So you have yourself Y, which is actually I, and you have yourself X, which is actually, actually, the imaginary part is how I denote it. Look at the syntax. Imaginary part. And X, which is the real part. Boom. And I have the real part here, E. Imaginary part here, B. And look at that. You have plotted yourself a nice complex number, E, B. Right. So why did they do that? Well, I have no idea why they do that, right? But here what I do know. What I do know is that it have certain characteristics that was very helpful from it. So I would take it that is what they were imagining in their head. The fellow who made this diagram right here, and then Cartesian plane, it is called the argon diagram, or complex plane, right? Right. So what we want to do here today, right, is to understand how the polar form relates to the argon diagram through its component parts, right? So in our polar form, right, we have something like this: cos of theta plus I sine of theta, R, where R is the modulus and theta is the arg Z, the argument of the complex number Z. Why do they call it the argument? Like, if it's an argument, I don't know. That's just the syntax. But we all understand in reality, it's theta, right? It's theta. Because what happens is that the argument of C is not measured the same way in which normal theta is measured. And we'll get to that later, right? So R, the modulus, here's the idea, right? So the modulus, so the reason why they want it in this form, polar form, right? What we call polar form, which is still equal to the A plus BI form, right? It's still equal to that, right? They're not different. The idea is that with this form, since we have it in a trigonometric form, right? You know, with cos of theta, sine theta, we could find some relationships, which is, and the more specific one, which is called the Moivre's theorem, allows us to do very quick computations that would take much longer if we had to use it this way. That is the main reason why we learn about polar form, right? The question is how they got the polar form. Well, they got the polar form through the Argand diagram. How? Well, here are the modulus, right? And we know that modulus, right? A modulus of z, right? Modulus z, so you have modulus of z. And what do we know the form of a modulus is the is Pythagoras theorem. So essentially they're asking you for the length. They're asking you for the length, which is this here, from the origin to the A and B. That is the modulus. And the reason why I call the modulus specifically because how we're gonna find it. And the way we're gonna find it is by Pythagoras theorem. If here this distance here we know is A, and this distance we know is B, and let's call this R, then R is equal to the square root of A squared plus B, which is the form of the modulus, right? The modulus of the length, right? R, which is the length from the origin to the point A to B, is what we call the modulus. Notice that we're not using I because in the context of the diagram we're asking for distance, and what happens, the I will make it be negative. And that's not the idea. The idea is just finding the length from, because what happens, you get a wrong answer. Okay, if it is negative, it will be A squared plus B squared, be A squared minus B squared, which will not give us the length. It will give us some negative value. Or it may give us a negative value, right? So now, so we have our R and theta, right, which is the measurement here. Boom. What happens is that theta now can relate B and A into cosine and sine. Because what happens is that we know our trig rules, right, and it's such that the ratio of B, right, imaginary part, and R is equal to the cos of theta, of the sine of theta. Therefore, B is equal to R sine theta. Same thing with A. A over R equals, in this case, cos theta. Therefore, A equals R cos theta. So what do we get? We get that if we sub A equals R cos theta and B equals R sine theta, then A plus BI actually equals to R cos theta plus I sine theta, which equals to R open brackets cos theta plus sine I sine theta. Right. Easy, right? And so, and what this does is relate, so if we analyze the difference, right, in terms of direction, because the idea behind a coordinate system is to locate something specifically, right? So say you want to go, say like in this case like a plot of land, and you want to go to that specific point in the land, you could say that you go in a certain amount of distance, right? Let me use the other one, so You want a certain amount of distance A, and you're going to a certain amount of distance B. And that way you can reach the point AB. Or you can find your length from the origin to that point. Well, actually, what you can do is take an angle, right, of how much theta it is, right, to line up to the point AB, and just go the distance of how long that distance between AB and the origin is. And you end up to the same point, and that's the idea. That's why they're equal. Now, and that is cool and all, but the point of using the polar form is because of its advantages over the Cartesian form. Should have mentioned that. Alright, so what do I want to do to you now? Now, okay, so the question is now, right? So let me compare and contrast. What happens when you geometrically multiply two complex numbers in polar form, right? So say we had z1 equals to 3 SIS 45 and z2 equals to 2 CIS 30, right? This here we're going to show you one of the first advantages of using polar form. Now here is a very short way to represent them, right? And so I'm using cosine. Just put C, and I represents the imaginary unit, and S represents sine. Shortened form, right? So let's do that. So they can, and 3 is obviously the the modulus. So z1 by z2, what I equals to 3 CIS 45 by 2 CIS 30. But obviously you can't leave it in this form, right? You have to turn back. So that is the same as 3 cos theta plus I sine, well not sine theta, but sine 45 plus. Now we don't want to simplify these answers yet. Well, not yet. Well, because we know if we simplify, we just get back to Cartesian form. And that's not what we really want here. Plus 45 plus I sine 45. Sine 30, I mean. So if you multiply that, well, if you take out those two, you have 6. And inside now you have cos 45, cos 30, plus cos 45 by I sine 30, plus I sine 45 cos 30, plus I sine, or I squared in this case, I squared sine 45 sine 30. Now here's going to happen. Here's something that's kind of magical, right? So you have this here. Let me simplify it a bit. So you have cos 45 or cos 30 plus, we simplify the I term, so there is I open brackets. But actually there is 2 of them, so there is 2 I. What are the chances of that? No, I not 2, but simplify it, and we get cos 45 dot sine 30 plus sine 45 cos 30, and then now watch this. Well, this become negative because I squared is equal to the square root of -1 squared is equal to -1. So you have yourself the negative of sine 45 by sine 30. right? Now, if we pair these two here, let's pair them. We have ourselves 6. The real term, they pair the real terms, right? Pair the real terms. Here, R of Z. So now you have cos 45 dot cos 30. Here's where the polar form becoming powerful. Huh? Sine 45. So I'm not saying you want to understand it. The idea is that the reason, I guess we would not polar form over, but the reason why we're still using it is because of its power. That is the reason, because of its power. Now look at the power now we're gonna have here. Look at the power. And then we can reflect. Now if you know your trigonometric rules, right? Your identities, you would realize that this is actually the what? What is the cos 2? This is actually a compound angle formula. For cosine. And this here, this is real lucky. I even know how to even see it's this realization. This is what I call realization. Realization is when it's just it's not like they knew it was gonna happen. It just happened. And it's so wow, amazing. Here you come back angle formula for sine. So now you can simplify this, and this is the compound formula. This will be cos. Let's simplify the cos 45 plus 30, and this here, my friend, simplify to I sine 45. Well, it should be negative. If it's negative, it should be minus sine 45 plus 30. I'll put that in brackets. So now you get yourself 6 cos 75 minus I sine 75. How are you supposed to get? No, it's plus. Right, plus. Hang on. It's plus, right. Right, plus. So look at that. So that means, so we saw a pattern there. So here's the backdrop. If you just have angle here, 45, angle here 30, for two complex numbers, right, in polar form, then the answer of the product, well, excluding the answer of the product would just be their modulus multiplied as normal, and then just to add the arguments. Hence, if I had, say, 4 CIS 30 by 5 CIS 75, then the answer is just simply 20 CIS 105. You see, you look at that. I didn't even have to think about that. Now say this that was a normal form, right? Say that was normal form. I don't know. Let's get a good example. I don't know. What would be a good example? I guess it's CIS 30 and let's say for CIS 30 by 5 CIS 60. Now this in the original form, right? That'll be for cos 30. So 4 cos 30 is that is root 3 on 2. And then plus I sin 30, so that'll be I. That'll be 4 sin 30, so that'll be 2I multiply. So this could cancel out, so you have yourself 2 root 3. And then this one will just be 5 cos 30, which is a half, so that'll be 2.5 plus sin 30, so that'll be 5 root 3 on 2I. If you have to multiply this, right, given that you have to keep these I terms, separate, then you'll have to use your distributive law and expand this, right, to get an answer. But in the polar form, my friends, all you have to do is just multiply these two bad boys here. This 20. And you get yourself CIS 90. You see that? Is that powerful? And then you know yourself, well, cos 90 is 0. So you're not just having cos 20 I sin 90. So it's 20I. So this will evolve to this will come up to 20I. Would it? It probably should. I have no idea. But that's cool. That'll come to 20I. As simple as that. So this is why we learn about the polar form in the first place. If we compare and contrast it between the two methods of having to use the Cartesian form to multiply and the polar form to multiply, it is just phenomenal how fast it is. Because of that compound formula that end up just resulting somehow through multiplying in polar form. After they notice this relationship, when you multiply two complex numbers in polar form, one Cartesian form. Polar form is the best thing. You know what I'm saying? Right. Now let us do I try to remember, let me do some retrieval practice. So we want to know what is the formula for converting a complex number to polar form. Our formula to turn this into that. Well, I didn't even put that. I could have put CIS there. See how fast that is? Down to that is that you find R, which is the square root of A squared plus B squared. And you find theta, or the argument of Z, which equals to the tan inverse of B over A, and must be more than, had to be less than or equal, had to be, theta had to be more than negative pi and less than or equal to pi, right? That's a rule. That's a rule, right? Now, why is that a rule? Now, because this is what made the argument of Z specifically important in they have to identify it differently because it's not just theta you're trying to find. And that's what we're gonna do a little bit just now. So you see, why is the modulus always positive? Because modulus measures distance. R measures distance. Therefore, it should be positive. I mean, it must be in a sense, but it should be, because why would it be negative? It's not per se. It's not like it's a measurement of speed, right? Because negativity, like sign, right? Negative. You see these signs here? And positive. These are indicator of direction. That's what they are. In terms of maths, in terms of like vectors and physics, like that. Negative and positive is just an indicator of direction. And distance has no direction. So it should be positive. Since this is a scalar quantity. And the formula also ensures that it's positive with a squared plus b squared. Because square any number, no matter negative or positive, makes it positive. Right? And now why does multiplying two complex numbers add the arguments? Well, that has to do. Now I can't say why, because saying why is kind of like saying why would imply more like why did this happen to just when we use the distributive law expanded into the compound formula for sine and cosine. That I can't really explain. That just happened. There's a realization, a phenomenon of complex numbers. It just so happened to be we didn't like manipulate it to be that way. It just occurred to be that way. So my explanation is that in order for the reason why multiplying two complex numbers are the argument is because it forms a compound formula for both cosine and sine theta, cosine and sine, right? Which, when simplified, represents the sum of the two angles. Okay, see the cosine, right? Okay, the cosine and sines, right, of the two complex numbers end up forming, right, compound angles with each other. Not separated, not like it's cos 30 minus sine 30, sine 30. Not that. It's that both of their angles, right, both of their trigonometric values end up multiplying with each other to form a relationship we know as the compound angle formula. And that we see when we simplify it to that form ends up adding the 45 and the 30, the two angles, which gets you the 75. So that is really why it happened. That's why you could say that the argument multiplying two complex numbers is really just adding the argument of them and multiplying the modulus of them. It just so happens to be that way, essentially. I don't know any other way to explain that. Right, now let's convert 4 plus 4i to polar form. Right, so we must find, to find polar form, we must find r, which is equal to square root of 4 squared plus 4 squared, which equals to the square root of 32, which equals to 2 root 2. Right? Now, it is 4 root 2. Because this converts to 16 by root 2. And then, to find theta, or the arc of z, well, that's equal to the tan inverse of 4 over 4, which equals to tan inverse of 1, which equals to 45 degrees, which is pi on 4. Therefore, the polar form Yeah. The polar form equals 4 root 2 CIS pi and 4. Simple as that. Now use the polar form to find z squared. Well, c is equal to this, right? So z squared, well, that's equal to 4 root 2 CIS pi and 4 squared. Now I don't know exactly what they mean by calculate, because I know they want I want a number, but I guess I want a number. Well, right. So this is the same as 4 root 2 CIS by 4 root 2 CIS. Hence, it is multiplying two complex numbers. Therefore, we just have to multiply the modulus, which is, that'll be 16. So I'll give it back to the 2, right? And then it's CIS, and just add these, so that is just pi and 2. Simple as that. Compare the geometric effects of multiplying 5 CIS 16. Geometric effects. All right. Okay. So I understand now. So let you compare, right? So I'm gonna just copy and paste that thing. Look over there. Well, compare the effects. I'm multiplying 5 CIS 60 and 2 CIS 90. Well, you get yourself, you just multiply the 2 modulus, so that is 10 CIS, you add these 2, so 60 plus 90 is 150. 150 is less than 180, so it's good. So if you go in the Venn diagram now, there you see. So you see you go in the Venn diagram, right? One position is here, because CIS 90, right, is essentially just I, right? So it'll just be 2I. So it'll be 2. So we have one of our points here. Let me zoom in. So one of our points is here. Boop. I am Z and REZ. A bit lower. Good. 2. And the next one was 5 CS 60. So that is like what? We meant that 6 degrees. 60 degrees is like here, around there, around here. And you're gonna 5, so around like here. Wrong here. So yeah, these two here. That's it. I think that is 60 around there, right? No. So that is, so I see that like 60 and I see as well the 90 together, right? Now when you multiply them, it stretch. This line here stretch, right? Wow, whopping. Well, in this case, I mean, depending on how you look at it. Yeah, it depends, right? So if you let this be z1 equal that and z2 equal this, we realize that z1, the r1 of z1 is stretched or scaled by 5 of R2 of C2. Let's see if that's correct. C2, and this is rotated. Right, so this here is 150. So it's rotated by an extra 90. Well, extra in this case, we're relating to this, so we add by extra. It's rotated by extra 60 degrees, so it's 60 here. So it's 150 in total. Rotated 50 degrees, 60 degrees, I mean, counterclockwise. All you know is not negative, well, because of the increase. The decrease, it will counterclockwise. By counterclockwise by RLC2. Yeah. So that's our answer for that. Kind of hard to say though. Well, let me see the next one. So you want to evaluate now, which is more efficient for calculating. Now, efficient has to do with time, right? You know what I'm saying? Time. How fast it takes you to do something. And the reason, right? The reason why polar form is much efficient is due to its advantageous properties, right? When multiplying two complex numbers in polar form, all you have to do is multiply their modulus or moduli. Moduli and add their arguments. as opposed to that in Cartesian form, which requires you to use the distributive law to expand and then simplify. This process is much longer and also hides an element of recognizing that I squared equals -1. Which means, hence it requires a lot of memorization of key attributes to simply find the final answer. Hopefully that sounds correct. So the reason why polar form is more efficient is due to its advantageous properties when multiplying two complex numbers in polar form. Because all you have to do is multiply the moduli and add the arguments, as opposed to that in Cartesian form, which requires you to use the distributive law to expand and then simplify. This process is much longer and also hides an element of recognizing that I squared equals -1. Hence, it requires a lot of memorization of key attributes to simply find the final answer. Yeah, because there's only two things you need to remember. Where distributive law, you have to account for multiplying this product by this product plus this product by this product. And then when you get I squared to me, I remember that, wait, I squared -1, so now it's a minus, and then you can simplify. That takes that's a long process. So the polar form is advanced. That's why, like, when you want to, we just not evaluate it, right? We just not found why polar form is more efficient. So that's why we learn about it. I mean, if polar form wasn't efficient, then scrap the idea, right? There must be a reason why we learn about it in the first place. And the reason we learn about it is because it has these advantageous properties. A certain man didn't find these properties, he could leave out the polar form and say, this is dog, wood, my bad. This is, dog poop. It sucks. Who cares? But we care now. It gets faster. Like a stronger engine or something. Better fuel. Using oil to prevent friction. It is something that allows us to do things more quickly, essentially, right? Nothing too major there. Create your own real world problem that involves the polar form. I see that. Big good. I mean, what real world problem I could do with that? I don't know. What do you mean to do all about? Wait, how am I supposed? How good I pass my time, bro? I'm supposed to. that's the session for today. I mean, not much else I can do. It's only the evaluation that's supposed to be doing anyhow. So, it's a good session. Have a good day.